So this is the lecture 3.2, where we will be introducing to you the concept of a wave equation. I will be briefly trying to explain to you what is the meaning of a wave equation. And of course, I will be trying my best to say that the wave equation is a differential equation. So some words regarding differential equations. And then we will form the wave equation and learn later words that the wave equation is essentially a second order differential equation. And then we are finally ready with the lecture. Then we have a final ready wave equation at our hand. So if we think of a physical systems and physical processes or phenomena, we are often thinking of a dynamic processes, meaning that they change when time evolves or when we go into a different location. And these kind of phenomena are often described by using differential equations. So some practical examples I could think about, for example, I could imagine radioactive nuclei and how they decay. So for example, the radiative decay is essentially a dynamic process, so that the nuclei change into other nuclei because they are radioactive. And this is a dynamic process. And if I would want to quantify what happens, I would need to form a differential equation to describe the dynamics. And if I would be able to solve the differential equation, I would have a piece of mathematics that would describe to me at a given instance of time how much I would still have the radioactive nuclei present in my system. Another example could be, for example, heat equation. That's a classical example of a differential equation. So for example, if I would heat up, let's say, a piece of a metal at the center of a bulk piece of a metal to, I don't know, let's say like 100 degrees of Celsius above the room temperature, and I would want to understand how it spreads the heat into the metal, I could use a differential equation, a heat equation, to describe this spreading of thermal energy into the system. So in that way, we can also understand these kind of dynamic processes. So it's not necessarily the case that we are thinking about temporal evolution, but we can also think of how things change when we go to different locations, in addition to possible temporal evolutions. And now what we want to do in our course is that we want to find a differential equation that would be describing to me how a wave would be propagating. And let's just now describe a propagation for the simplicity only along the plus minus z directions. And then we will generalize things later on. And thinking of the mathematics, we know already, we have discovered what is the functional form of a moving perturbation, so that the solutions of the wave equation, the psi's, the wave functions, and now they are of course parameters of two variables functions of two variables, so of variables z and t, so that we know the functional form must be of something that in the argument we have a functional form of z plus minus v times t. So this gives me the time dependence or the link between the spatial coordinate z and the time t, such that now this wave is actually propagating into the direction of z at the velocity of v. And I can denote this z plus minus vt as a new variable z prime. And now I know that I have a wave function psi that depends on a single variable. And let's now start differentiating this wave function psi over the position z and the time t to see what we come up with, and then hopefully at the end of the day we can have a wave equation at our disposal. So what we have is that we can calculate the partial derivative of our wave with respect to the coordinate z, and we can just calculate this because we have the functional form is that we can just calculate the partial derivative of the function f with respect to the new variable z prime. And then, of course, we need to calculate what is the partial derivative of z prime with respect to the z. So in essence, what we do is that we start differentiating this guy. And if we want to differentiate this function f of function z prime with respect to z, as we do here, then we must take the partial derivative of over z prime, and then also we must take the partial derivative of z prime with respect to z. Or another way of looking at it could be that we just add and divide this partial z prime term into here. Mathematicians would not like this kind of thinking, but for us physicists, when we are thinking about these differentials, and this also works us quite well for us, so that we can really imagine them as a normal kind of numbers or normal kind of parameters, and we can just multiply with them and divide them with ease without worrying too much about the kind of mathematical lack of rigor in this approach. Okay, so we know how to calculate this partial derivative of z prime with respect to z. If the functional form is this, so that we know that definitely that equals to unity, so that we are left with the partial derivative of f with respect to z prime. So in essence, we recall this relation between the z prime with z and t, so that when we calculate the partial derivative of z prime, we see that of course we have the unity in here. Now let's do the same, but now we differentiate with respect to time. So we calculate the partial derivative of psi with respect to time, and now we do the same thing, so that what we are left with is that now we want to calculate the partial derivative of z prime with respect to time. And now we have something else in here, because we have this multiplier plus minus v in here in front of time. So what we have left is that we have plus minus v times the partial derivative of function f with respect to z prime. And now we can combine these two equations, and we get a kind of a differential equation that would describe some kind of physics here, but this is not yet a wave equation that would satisfy our needs. So essentially, we just combine equations. So we divide this term to the left-hand side, and then on both cases, we have on the right-hand side same kind of terms. So we equate them together, and then we have the partial derivative of psi with respect to time equals plus minus v of psi over dou z. The trouble here is that we have this plus minus term there, and if we would be looking for solutions, depending on the direction, the waves would propagate differently, and this is somehow not the best scenario in terms of physics, because most of the time in physics, the propagation of light doesn't really depend on the direction, so it should propagate equally well to the right hand side as well to the left hand side. So if light propagates on the plus z direction, it should propagate equally well for the minus z direction. This is the meaning, especially in a homogeneous medium. So that there is a problem that this description is not yet best to describe something physical. And we know from the physics point of view that these solutions and what kind of wave functions we get out of the wave equation, like how they propagate, it should not depend on the chosen coordinate system. And the solution, how do we get forward? And this is always the case in physics. When the simplest approach does not work, we go into the next simplest case we can imagine. And our solution this time is to go into a higher order differential equation. And now we just take this and we get similar to equations as before. But now instead of taking the first derivative, we now take the second partial derivative of psi with respect to z. And then what we are left with is that we are still having, we know already what was the first partial derivative. So we now take the second partial derivative, and we're still having this term here. And as before, this is unity, so that we are essentially left with this guy on the right hand side. So this is essentially just exactly as before. But instead of now the first order partial derivatives, we actually have the second order partial derivatives here. Things get slightly more interesting with respect to the derivation over time. So when you take the second derivative of psi with respect to time, we have the first original plus minus v term, and now we must also take the second partial derivative of our function, and now we again have this partial derivative of z prime with respect to time. So we have additional plus minus v term in here that now changes things. So now what we have on the right hand side is that we have the plus minus v to the power of 2, and then we have the second partial derivative of function f with respect to z prime. Sorry, there's a typo. It should be z prime there, here inside the denominator. So now we combine these two equations as before, and now we can really form a wave equation. And what's nice for us and what we were wanting to see is that now the solutions do not depend anymore on the choice of the coordinate system. So we have second partial derivative of psi with respect to the z, and this is equal to 1 over velocity squared times the second partial derivative of psi over t. And here psi, our wave solution, our wave function, our wave, is a function of two variables of z and t, and the functional form is such that their relative dependence is of form z plus minus v times t, in order to ensure that the wave actually propagates along the z direction with this velocity of v. So what we learn here is that, of course, for this psi, we do not yet know how exactly this looks like, but at least we definitely know from here that we have this kind of wave equation, this kind of differential equation that we are dealing with. We know that this psi must be twice differentiable so that we can actually have a proper solution. So we already know a little bit about physics, that what we could be, or what kind of physics we are seeking, or mathematics we are looking at when we are forming a solution for the wave equation. So wave must be differentiable twice so that it can actually be a solution of the wave equation. So this is what I wanted to say here. So thank you for your time, and next we will actually go and find some kind of simple solution for the psi, how it actually looks like, what kind of functional form it has, and then we will slowly build upon that to finally understand how we can really understand propagation of electromagnetic radiation into an arbitrary direction. So thanks for listening, and please follow me quickly into the next lecture. Thanks and bye-bye.